Hi, hello everyone, and welcome back to my YouTube channel Sporify Learn. Today, let's start with the second PUC, second chapter in chemistry, that is electrochemistry. Let's see the NCRT line by line. First, what they have given. What is electrochemistry? Let's understand. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring out non-spontaneous chemical transformations. Here, what they are trying to say is that, see, it is the study of electrochemistry. It is saying that it is a subject or a part of chemistry, that is study of production of, see, electricity from energy released during spontaneous chemical reactions. That means that happens quickly. Spontaneous is nothing but that happens very quickly. And let's try to understand next point. And the use of electrical energy to bring non-spontaneous chemical reaction transformation. See, first they had given as electrical energy from energy released during when spontaneous chemical reactions will be taking place, the production of electrical energy will be produced, right? That is, and non-spontaneous, like it is nothing but when we have to use of electrical energy, like when this non-spontaneous chemical transformations is taking place, the use of electrical energy. Okay, and if we see the spontaneous, what is spontaneous means without addition, like it happens very quickly and we cannot add any extra addition like external addition to it, that is termed to be spontaneous. And non-spontaneous is obviously reverse of that. We have to add something addition in external. And the subject is of importance both theoretical and practical. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Battery and fuel cells convert chemical energy into electrical energy and used in large very scale, like they are used in various instruments and devices. The reactions that are happening, right, they are carried out electrochemically and can be energy efficient and less polluting. They are energy efficient and less polluting. This is very important point. Energy important and less polluting. Therefore, study of electrochemistry is important for creating new technologies. Okay, and it is a very vast and interdisciplinary subject. In this unit we'll discuss about that. First, they have given about electrochemical cells. We had studied the construction and functioning of Daniell cell. Okay, see, if we see this, this is the Daniell cell, that is having electrodes of zinc and copper. Okay, dipped in solution of their respective salts. Okay, these are salt solution. Now there is a salt bridge in between that. In zinc and in copper, the current is passing, and the current is passing from copper to zinc, and the electron flow is happening from here. It is going till here and it is coming here. Okay, that is the flow taking place here. And if we see, this is copper, this is salt of zinc. Now if we see the reaction, that is Zn of S, Cu2 plus gives Zn2 plus plus Cu. I hope you know to how to balance the reaction. Next is here, the how I'll say, here one zinc is there, here one zinc is there, it is correct. Here one copper is there, here one copper is there, correct. That is how we balance the reaction. When we have to convert to electrical energy and has potential 1.1, when concentration of Zn2 plus and Cu2 plus ion is unity. Unity means 1. Unity means 1. Okay, sorry, unity means 1. Okay, now that is called as galvanic or voltaic cell. And if we see another important point, like it is happening as electrolytic cell, a device that for using electrical energy to carry non-spontaneous chemical reaction. That means that do not need external addition to which to perform its reactions. Both type of cells are quite important and we shall study that. Now let's see about the galvanic cells. As mentioned earlier, a galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. This is the definition of, sorry, from here, it is the definition of galvanic cell. And next, in this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work, which may be used for running a motor or other electric gadgets like heater, fan, and geyser. Daniel cell discussed earlier is one of that such. Zn, the reaction which we wrote, and if you see Cu plus 2 electrons gives Cu to balance, 2 electrons is reduced, and here 2 electrons is oxidized. And if we see that half cells or redox couples, the two portions that are called. And if we come to the next important point, a potential difference, a potential difference develops between the electrode and the electrolyte, which is called electrode potential. That is called as electrode potential. When the concentration of the cells, all the species involved in a half cell is unity, that is termed to be standard electrode potential, or we call it as SEP. Okay. According to IUPAC, in first PUC we have learned about that, right? IUPAC name and convention, standard reduction potential are now standard electrode potential. Okay, in there will be anode and there will be one cathode for reduction and this for oxidation. And there exists a solution between the two electrodes, and the direction of current flow is opposite the direction of electron flow. See here, current is flowing and electron is flowing here, so though both opposite direction. The potential difference between two electrodes of galvanic cell is cell potential, and it's measured in volts. And the symbol is V. The cell potential is the difference between the electrode potential of cathode and anode. It is cell called the cell electromotive force, or CEMF. This is one of the most important term to understand here. The difference between electrode potential and of cathode and anode, that is called as EMF, cell EMF. Okay, EMF is nothing but electromotive force of the cell. When no current is drawn through the cell, it is now an accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. And if we see the reaction, E cell is equal to E right minus E left. And if we see the cell reaction, it is Cu plus 2Ag gives Cu2 plus 2Ag. See here, 2Ag, 2Ag is here, 1 copper, 1 copper. So it is balanced. And if we see the half cell reaction, that is cell reaction, half cell reaction is 2Ag plus 2 electrons give you 2Ag, that is reduction. Cu2 plus 2 electrons here, oxidation, and this is reduction. Now, the potential of individual half cell cannot be measured. We can measure only the difference between the two half cell potentials, that gives the measure of the EMF cell. Okay, if we arbitrarily choose the potential of one electrode half cell, that is half cell, then the other can be determined with respect to this. See, according to the convention, a half cell called standard hydrogen electrode is He, represented by platinum H2 hydrogen H plus. It is in aqueous, gaseous, and solid, is assigned a zero potential at all temperature corresponding to the reaction, that is H plus give plus electrons gives half H2, that is reduction. Sorry, yeah, it is happening reduction, right? Yes. Next, if we come to the next topic, they have said as at 298 Kelvin, the EMF, that is standard hydrogen electrode, second half cell, and if we compare that, it is constructed and we have to include a this. Okay, between this is here is first and here it is second. And now if we see E naught is equal to E right, E naught right minus E naught left, and E naught is equal to E naught R minus 0, that is E naught R. And if we see platinum solid H2G, that is gaseous, 1 bar is considered, H plus aqueous solution 1 molar, and Cu2 plus aqueous 1 molar, and Cu. And now if we see, these all are the reactions that we have to study. The standard electrode potentials are very important, and we can extract a lot of useful information from them. The value of standard electrode potentials for some selected half cell reduction reactions are in the table. Okay, we will discuss that table. Now the table indicating fluorine gas and fluoride ions, and therefore fluorine reducing agent. See, let's discuss where is table 2.1, right? They said table 2.1. Yeah, see here, this is the reaction that they have given in the reduced form, and the electron E naught value in volts. Okay, F2 of G plus 2 electrons, that is oxidation, 2F minus, and CO3 plus plus electron give you CO2 plus H2O2 plus, this gives you 2H2O. You can go to this whole table. They have given the reaction that is oxidized from Ne minus and reduced form of it, and the value. Now let's see the Nernst equation. This is one of the most important topic. We have assumed in the previous section that the concentration of all the species involved in the electrode reaction is unity. Unity means one, we know. This need not to be always true. Okay. Nernst showed that for the electrode reaction, Mn plus Ne, that is number of electrons they have given as N. Okay. Don't get confused. M. Okay. We should give you M, because if you take uh, Cu 2 plus plus 2 electrons will give you Cu. Okay, because it is reduced. And now if we see the standard hydrogen electrode, this that can be represented EMN plus or M, that give you E naught Mn plus M minus RT divided by NF log, and len or log you can take M divided by Mn plus. Okay, now we will see what is RT and all later, and that is, but concentration is this have already defined. R is gas constant, T is temperature in Kelvin, F is Faraday's constant, that is, remember this value 96487, and Mn plus is the concentration of the species Mn plus. Now if we see in the Daniell cell, that is for cathode E, if you take for copper, it is Cu2 plus Cu minus RT divided by 2F ln 1 divided by Cu2 plus. Okay, now why it became 1, you see the formula here. M value is what we have taken, copper value is 1. So, and now for zinc and for cell potential, so you can see the Nernst equation can be written as E cell is equal to E naught cell minus RT divided by 2F ln Ni2 plus divided by Ag plus 2. See, for this they have given. Okay, and for different Nernst equations they have given. Now equilibrium constant from Nernst equation. In the Daniell cell, it is closed that Zn plus Cu2 plus Zn2 plus aqueous plus copper takes place as time passes, and Zn2 plus keeps on increasing while the concentration of it is inversely proportional, and at the same time voltage of the cell can read an voltmeter keeps on decreasing, and there is no change. E cell is equal to 0 is equal to E naught cell minus 2.303 RT divided by 2F log Zn2 plus plus divided by Cu2 plus, because here it is NF, right? We know the formula, and equilibrium constant, so we write it as NF, 2.303 RT divided by NF log Kc. And this is the important formula you have to remember, so I'll mark it. electrochemical cells and gives energy of the reaction. Electrical work in 1 second is equal to electrical potential multiplied by total charges passed. Okay, now if we see, to obtain maximum work from galvanic cell, then charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore if the EMF of the cell is E and NF is the amount of charge passed, then delta R, that is change. If you see, the delta is nothing but the change of which we are taking, that is Gibbs energy of, then it will give delta Rg is equal to minus NFE, that is cell. Okay, now the reaction can be written as Zn plus 2 Cu2 plus gives Zn2 plus Cu. Okay. Now the states are also changed, you can observe, and the value is being exchanged, that is changing. Now the value will be delta R G naught will be equal to minus RT ln K. Conductance of electrolytic solutions. We know Wheatstone bridge in physics chapter, current electricity chapter. It is necessary to define a few terms before we consider the, see, R is nothing but resistance, right? R is nothing but resistance, and ohm, it is measured in ohm, right? Let's write on here, R is measured in ohm, and SI unit is kg meter per second, or SQA square, and it can be measured with the help of Wheatstone bridge. Yeah, it is studying in physics, as I said, and that is directly proportional to L and inversely proportional to area of cross section, that is, you can say L divided by A. You know this formula, and if you want to remove this proportionality symbol, you have to add one constant, that is called as rho. You can draw like this, L divided by A. You can take small l also. Now the resistivity SI unit is see what they're saying is Greek, that is rho we have taken is called resistivity, right? The whole this which we came, this is resistivity, and its meter is ohm meter, and quite often, and IUPAC recommends, see, 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01. See that you have to divide 1 divided by 100 will give you 0.01, and the inverse of resistance is called conductance. Okay, inverse of resistance is called conductance, that we have is equal to G, that you can write it as A divided by L, that is rho you have to add for constant, and you can take this A divided by L and you can keep this here. Okay, now the SI unit of conductivity is, the SI unit is Simon, right? S Simon, and ohm per ohm is the SI unit of this Simon, and mo or ohm inverse, right? So if you read from last MHO, so more we say that, and that is 1 Simon per centimeter is equal to 100 Simon per meter. This table you can read this material conductivity, and material its conductivity they have given all sodium, copper, silver, gold, and all. And now if we see the electrical resistance through metals is called metallic or electronic conductance, and is due to the movement of electrons. The electronic conductance depends on the nature of and structure of the metal, the number of valence electrons per atom, and the temperature. Now, as the electrons enter at one and go out in the other end, the composition is remain unchanged, and we already know that for pure water that has small amounts of hydrogen and hydroxyl ions, that is 10 power minus 7 molar, which lend it very slow conductivity, and the conductance of the electricity by ions present in the solution is called electrolytic or ionic conductance, and it depends upon the nature, size, the nature of solvent and its viscosity, concentration of the electrolyte, and the temperature. Now if we see the measurement of the conductivity of ionic solution, We know that the accurate measurement of unknown resistance can be performed on a Wheatstone bridge. In that, there will be resistance L by A, that is area of cross section and the length. Firstly, passing direct current, that is DC, changes the composition of the solution, and if you have alternative current, that is source of power, and it will feel in difficulty. So that is conductivity cell. If we see, there are two types of conductivity cell. See, first is connected by wires. See, here it is connected by wires, and there is platinized platinum electrode, and here also platinized platinum electrode. And here you can see there are connected like this, and the wires are connected being like this. Here they are all in one end. Here there are two ends. Okay. Now that is R is equal to rho L by A, that is K divided by A, and g naught g star, that is cell constant, that can be written as L by A, that is equal to R K. Now see, this is the Wheatstone bridge. You will be having resistance, and here it is the, this is also a resistance, that is a conductivity cell, and here is R1 and here is R2, and middle is P and this is O. Now we can see O is nothing but the oscillator, and P is the detector that we have used. R2 is equal to R1 R4 divided by R3. See, if you want R2, they have said R1 R4, that is this and this, divided by R3. K is equal to cell constant divided by R, that is G star divided by R. See, here we saw, right? See here, yeah, cell constant. Now, molar conductivity, if we want, that is nothing but the physical more meaning quantity, that is of the concentration of ions, that is in with the ions that move under the potential gradient, that is termed to be molar conductivity, that is this term to be as this divided K divided by C, and it is expressed in Simon per meter, and the concentration is 1 molar per meter cube is said to be 1000 liter per meter cube, and into molarity, that is mole per liter, and one, you can see this two conversions. And variation of conductivity and molar conductivity with concentration, the conductivity always decreases with decrease in concentration, both for weak and strong electrolytes. See, conductivity, I'll write it as COND, conductivity. Conductivity is decreasing with decreasing concentration, so if it increases, it increases only, right? So they both are directly proportional. And the conductivity of a solution at given concentration is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section, that is A, and that can be represented as K, and we can write that as is equal to Ka by L, that is equal to K. And you can see this graph in x-axis, there is mole per liter whole power 1 by 2, and because we have taken in 0 0.2 0.4, that is in decimal values, and here it is Simon centimeter cube per mole, that is in 200 400, and it is being decreased, that is potassium chloride, and now we can see that is limiting molar conductivity. Now if we see Kohlrausch law of independent migration of ions, he states that limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of the anion and cation of the electrolyte. Thus, see, this is lambda. This is lambda. Sodium plus and chlorine minus are limiting molar conductivity of the sodium and chloride ions respectively. Then that can be written as, see, that molar conductivity of NaCl is equal to lambda naught Na plus lambda naught Cl minus, and that applications, if we see where it is applicable, it in migration of ions. It is possible to calculate molar conductivity from lambda naught ions, and moreover for weak electrolyte like acetic acid, it is possible to determine the value of dissociation constant once we know these two value at a given concentration. Electrolytic cell and electrolysis. Now let's see what is electrolytic cell. Electrolytic cell, external source of voltage, is used to bring out a chemical reaction. That process are of great importance in the laboratory and the chemical industry. One of the simplest electrolytic cell consists of two copper strips dipping in aqueous copper sulfate. If a DC voltage is applied to the two electrodes, then Cu2 plus discharges to the at the cathode, and the following take place. Cu2 plus two electrons give you Cu, and Cu plus Cu2 gives Cu2 plus two electrons, and reduction and oxidation is happening. If we see Faraday's law, Michael Faraday was the first scientist who described the quantitative aspects of the electrolytes. Now let's see what are the flows. His first law was the amount of chemical reactions which occur at any electrode during the electrolysis by a current is proportional to the quantity of electricity passed. Okay, now he's saying that the amount of chemical reaction which occurs, right, at any electrode, it may be cathode or anode, during electrolysis, it is proportional to the electricity quantity passed. And second law is that the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent, that is atomic mass of metal divided by number of electrons to reduce the cation. This is Q is in coulombs and I is in ampere and T is in second, because I is current and T is time, as you all know. And the quantity is measured in Faraday, right? So the symbol is F. And now let's go on to the next topic, that is product of electrolysis. That depends on the nature of material that we have and the types of electrode that is being used. If the electrodes is inert, that is platinum or gold, it does not participate in chemical reaction and acts only as source or sink for electrons. On the other hand, if the electrode is reactive, that is for inert, and it is reactive means it participates and the product will be reactive and inert. You can see all these reactions. See, let's see NaCl, that is sodium chloride of aqueous, that gives you in on water, that gives you Na plus of aqueous solution plus Cl minus. At cathode, H2O plus electrons give you half H2 plus OH minus. And see, in order to balance, we have added here half, because 2 and 2 can get cancelled and one hydrogen can be remaining. Anode Cl minus give you half Cl2 plus electrons. Batteries. See, let's see what are batteries. Any battery, usually it may have one or more than one cell connected in series, or that can be used as source of electrical energy, is basically galvanic, or that for redox reaction. And see the battery, primary batteries, there are two types of batteries. In primary batteries, the reaction occurs only once, and after the use of over period, it becomes dead and cannot be used again. Okay, now that is Leclanche cell and its discoverer. Let's see, that is dry cell. Okay, then that is common in our transistor and clocks. That is having carbon, that is graphite rod, and surrounded by powdered manganese dioxide and carbon. The space between is ammonium chloride, that is NH4Cl, and zinc chloride ZnCl2, and the equations at anode and cathode. See, this is carbon rod at cathode, and zinc cup, that is anode, and the manganese powder, carbon black, and ammonium chloride paste, all are present here. This is the primary battery, that is dry cell. And now if we see the mercury cell, suitable for low current devices like hearing aids, watches, consists of zinc mercury amalgam as anode and a paste of HgO and KOH, potassium hydroxide, zinc oxide and all, and you can see these both reactions. That is secondary batteries. Primary batteries is that, secondary batteries is that is having this anode and this is the anode cap, and cathode is present which is in blue component, and this is cell can, the whole is cell can, and this is the gasket that we have, and this is separator between this, okay, anode and the cathode, that is having PBS, that is lead SO4 to PbCO SO4 minus 2 plus 2 electrons, and PbO2 plus SO4 2 minus plus 4H plus 2 E minus, that gives you PbSO4 plus 2H2O. This is lead storage battery. It is also one of the most important. You can see this diagram. And next concept is fuel cells. Production of electricity by thermal plants is not very efficient method for the, and it is major source for pollution. See that the electricity by thermal plants which is happening, right, that is having very causing the more pollution. So, in such plants, the chemical energy, that is heat of combustion of fossil fuels, is first used for converting water into high pressure steam. So that that is coal, gas, or oil, and this is used to run a turbine to produce electricity. And we know that galvanic cell directly converts chemical energy into electrical energy, and the galvanic cell that are designed to energy of combustion of fuels, sorry, fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. See, this is the fuel cell of hydrogen and oxygen is entering. This is the aqueous electrolyte. This is cathode plus, anode minus, H2O. Corrosion. It is nothing but the slowly coats the surfaces of metallic objects with oxides or other salts of the metal. Okay, the rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships, and to all objects made of metals. In corrosion, metal is oxidized by loss of electrons to oxygen and formation of oxides. The See, the chemistry of corrosion is quite complex, but it is may considered essentially as a electrochemical phenomenon. Okay, at a particular spot of an object made of iron, oxidation takes place, and that spot behaves as anode. We can write that as because it is anode, 2Fe gives iron, right? We are taking, so iron symbol is Fe. 2Fe gives 2Fe 2 plus 4 electrons, and value of E naught is 0 minus 0.44 volts. Now at cathode is O2 plus 4H plus 4 electrons gives 2H2O, and this value is 1.67 and this value is 1.23 ferrous. Now this is how, and let's see the summary quickly. We studied about electrochemical cells, galvanic cells, what is spontaneous, what is non-spontaneous, as I said, and SHE and SEP, that is standard electrode potential, hydrogen electrode, equilibrium constant, conductivity, that is K, and molar conductivity. And about batteries, two types of batteries, fuel cells, electrochemical phenomenon, and hydrogen economy, and Faraday's law and all. And you can see these exercises, and thank you for watching the full video. Please make sure to like, share, comment and subscribe to my YouTube channel. And also I have an Instagram page called Sporifii_learn. You can go and follow, and you can get any materials if you DM me on Instagram. Thank you for watching the full video. Please make sure to like, share, comment and subscribe. Please do share with all your friends who can see, and stay tuned.